Hello students, welcome to the world of chemistry. This is Dr. Vikram Panchal and I am dealing with spectroscopy for chemistry. This is the chapter on IR spectra and lecture number 6. In this lecture, I will explain you a little bit in detail vibrational modes. Before that, I think I made a mistake in lecture number 4 where I was explaining about the types of bands appear in infrared spectra. So let me clarify this first. So when we plot a graph of IR spectra, it is always wave number versus percentage transmittance. So on y-axis we take percentage transmittance from 100% to 0%. So it is opposite of absorbance. So we can take when a percentage of transmittance is 100%, then absorbance will be 0. And when percentage transmittance is 0, the absorbance will be 100. So with reference to this, let us understand how the bands appear in infrared spectra. So normally what happens when molecule absorb infrared radiations, then if polarity of any polar bond changes, then it produces a signal or band. Okay, so there are mainly three types of bands. May go like this. Suppose this band goes like this. Here you can see the percentage transmittance is less than 20 or percentage absorbance is greater than 80, then this band is known as strong band. Okay, it is not percentage transmittance greater than 80, but it is less than 20. So it goes down. Okay, below 20, then we can consider these as a strong band, and for that we use S. Okay, next, suppose absorption of infrared radiations produce a band like this. Okay, then here you can see that percentage transmittance is between 40 and 60, or percentage absorbance between 60 and 40. Then it is known as medium band. Okay, and for that we use M. Next, if absorption of infrared radiation is like this, so that bands are here only, where percentage transmittance can be seen nearly 20 or less than 20, okay, or percentage nearly 80, not 20, or percentage absorbance may be nearly 20, then this type of band is known as weak band. Okay, and for that we use W. So this was the mistake I made in this percentage transmittance in lecture number 4. So just make it clear. Okay, so this is the case for infrared band: strong, medium, and weak. Okay. Next, I was supposed to explain you the vibrational modes in this lecture. So let us go on this topic now, vibrational modes. But before that also, I explained you this in previous lecture. I'll just repeat it once again, that there are three types of motions. Which one? Translational, next vibrational, and rotational. And each one will be in 3 dimensions. So translational motion in 3 dimensions, Similarly, vibrational motions in 3 dimensions. And rotational motions also in 3 dimensions. This which I was explaining you in the previous lecture. Okay. Like translational motion. So one particle or one molecule or one bond may move from one end to another end. This is translational motion in one direction. It can be in X direction, it can be in Y direction, or it can be in Z direction. Therefore, these are 3-dimensional translational motions. Okay, so that is similarly rotations also will be in 3 dimensions, that molecule keep on moving or rotating like this. For example, if we take one molecule which is made up of different atoms, obviously this bond will be polar and they keep on moving, rotating in different directions. This is the rotation in this plane. Similarly, there will be rotation in different plane like that. Okay, so these are rotational motions in different planes. Okay, like this. And these are called 3-dimensional rotational motions. For if number of atoms are n, then we need 3n degrees of freedom. So the term used to express different types of motions are called degrees of freedom. Okay, and here we need 3 degrees of freedom for translational motion and 3 degrees of freedom for rotational motions. So the remaining that is 3n minus 6 degrees of freedom used to explain the number of vibrations. Okay, so to explain number of vibrations, let us take one example. Over here, so for example, H2O. And H2O is non-linear molecule. You know, it is angular. The shape of H2O is like this. So it is non-linear molecule plus this bond is polar. Okay. Here, number of atoms. 2 hydrogen, 1 oxygen, so total 3. Okay. So number of possible vibrations will be according to formula 3n minus 6 for non-linear molecules. Here n equal to 3, so 3 into 3 minus 6, which will be 3. So there will be 3 types of motions, vibrational motions in H2O. This is the way we can explain it. Okay. Now we'll take another molecule, which will be linear molecule. Remember, in linear molecule, all atoms will be on one axis. And when all atoms are on one axis, you know, one rotation should be neglected. For example, carbon dioxide. Okay, here all oxygens and carbon remain in one plane, so this is a linear molecule and both oxygens are at equal distance from carbon, and both bonds are particularly non-apolar, but overall molecule is non-polar because effect of this polarity is in opposite direction. So here number of atoms are 3 again. But in this linear molecule, if we want to find out number of possible vibrations, then it cannot be 3n minus 6. Why? Because one type of rotations will be neglected, which will be on its own axis. Okay, so number of possible vibrations will be given by this formula 3n minus 5, and here n is equal to 3. So 3 into 3 minus 5 equals to 4. So in carbon dioxide, we will observe 4 types of vibrations. Okay. So here there will be 4 types of vibrations. So in case of linear molecule, like carbon dioxide, all atoms lie on a single straight line. Hence, rotation about the bond axis, which will be like this, is ineffective, or rather not possible. Therefore, only 2 degrees of freedom are necessary to describe rotations. Okay. So for linear molecules, that is why for linear molecules, degrees of freedoms of vibrations will be 3n minus 5, and for nonlinear molecules it will be 3n minus 6. Okay, so this way we can find out total number of vibrations according to this formula. Okay, in next lecture I will explain you different types of vibrational modes. So thank you so much.